Welcome back. We're doing another transport problem. And this problem states that an ideal gas mixture in a piston cylinder assembly has a molar analysis of 30% carbon dioxide and 70% nitrogen gas. The mixture is cooled at constant pressure from 425 Kelvin to 325 Kelvin. Assuming constant specific heats evaluated at 375 Kelvin, determine the heat transfer and the work, each in kilojoules per kilogram of the mixture. Okay, this is actually a quite tedious problem. The first thing what we're going to do is just define our variable. So the first thing that I notice is that it's constant pressure. So what we're going to say is P is constant. That means that no matter what state the control volume is, so in this case the control volume is in this piston cylinder assembly, so this is our control volume, no matter what state that is at, the pressure is constant. And we're told that it's cooled down, so we can say that T1 is 425 Kelvin, and it's cooled down to a state of 325 Kelvin. And we're told, which is actually a big hint on how we're going to go about solving this problem, is that the specific heats, so we'll leave it as C, I mean it could be a subscript of V or P, depending on how we're going to solve this problem, is constant at 375 Kelvin. So more than likely this is going to deal with linear interpolation, but sometimes it's useless to do linear interpolation because the change is relatively small if you just estimate of what it could be. But we'll see what I mean when we get to that part of the problem. So as I said before, the first step usually in these type problems dealing with mixtures is to find the mass fraction of each component because it may be useful later on. So let's define our table. So this is going to be the chemical. So we have a carbon dioxide and then nitrogen gas. And then we have the molar fractions. So that's going to be 0.3 and 0.7. And then we're going to have the molar masses of each component. That's going to be 44 kilograms per kilomole and 28 kilograms per kilomole for nitrogen gas. And then we want the weighted average, so to speak, of each component. So that's Mi times Yi. That's going to be 13.2 kilograms per kilomole for carbon dioxide and 19.6 kilograms per kilomole for nitrogen gas. And then we're going to have the mass fraction of each component. Now, before we could do that, again, we have to solve, or not solve, but find the average weight or the molecular weight of the mixture. So what we do, we sum up the components, the Mi, Yi, and that'll give us the mass or the molecular weight, the weighted average of the mixture. And that's going to equal the sum of this column, which is going to be 32.8 kilograms per kilomole. Now to find the mass fraction of each component, what we do is take this value and divide by this entire molecular weight of the mixture. And we repeat the process for each component. So what we do, what we get is 0.402, and this is going to be 0.598. Okay, so that should be simple enough. So that's usually the first step to these problems, and that's because we want to find the mass fraction just in case we might need to switch from mass to molar analysis. So we'll keep that as it is now. So our next goal is to find the heat transfer and the work. Okay, so the first thing to know when it comes to this problem is that it's a closed system. The control volume is a closed system. So what that means is that heat can be transferred, but mass cannot be transferred. So therefore, the mass within the control volume is constant. So the only thing that can be exchanged with the surroundings is heat and work being applied onto the system, or if the system is applying work to the surroundings. So a simple energy balance is used to find the heat transferred as well as the work. So let's just write out basically the first law of thermodynamics. So the first law is basically the change in internal energy is equal to heat transferred minus the work being applied onto the system. So before we move on, I like to define what I mean by positive and negative, and this is usually the convention for most textbooks as well as problems. So let's say this is our system, and if we get work coming out from the system, we define that as positive, and if we have to put work into the system, that is negative. And then it basically, for heat, it's the complete opposite of work. So what we say is that heat going into the system, that is positive, and then heat leaving the system, that is negative. And then for these definitions, this is the equation you write for the first law of thermodynamics for a closed system. Okay, for an open system, this equation is not as simple as this. It becomes time dependent, and it involves derivatives or time derivatives for that balance. So this is a closed system, so it's just a very simple first law of thermodynamics. Another way we can write this is in terms of specific internal energies and specific heat transferred and work transferred. So what I'm trying to say is that we can define this as little u, little q, and little w. So now these are values, intensive values that are divided by mass. So what that means is that to get the total amount of internal energy or work or heat, all we have to do is multiply these terms by mass, and we'll get that value. Usually it's a lot simpler just to work in terms of intensive properties, so we're going to use this right now. Another thing you may remember from thermodynamics is that the work can be defined as from one state to another of the pressure times the specific volume, or the change in specific volume. And what's special about this equation in this case is that the pressure is constant. So what we can say is that the work done from state 1 to state 2 is simply the pressure times the specific volume at 2 minus the specific volume at 1. We have enough information to calculate the work done onto the system or the work being done by the system to the surroundings. And the reason why I say that is that we could use the ideal gas law. That's a very common thing in this problem, is using the ideal gas law and recognize what it means and what are these variables, how can I use them. One thing to remember is that density is equal to 1 over the specific volume. So what that means is that the specific volume is 1 over the density. So what we're going to do is basically plug that into this equation, but not yet. What I want to do is relate this density to the ideal gas law. So what we can say is that the pressure is equal to times the density of the mixture times the specific gas constant times the temperature of the mixture. So this is all in terms of the mixture, not in terms of the components of the mixture. So what we can do is solve for rho. So now to plug in back into this equation, we just have to plug in these values based on these definitions. So we said that the specific work is going to be P times 1 over rho 2 minus 1 over rho 1. Therefore, by using the ideal gas law, what we can say is that this is going to be P times R times T2 over P. Remember, P is constant, or the pressure is constant, so that's just P. Even though you could say P1 or P2, they're the same. So this is going to be our T1 times P, and this further simplifies to something fairly simple. That's the specific gas constant times the change in temperature. So if we plug in the values for this, we can find the how much work is being applied onto or by the system in terms of math. We can say that the specific work is going to be, and this will give you negative 25.348 kilojoules per kilogram of the mixture. So it's really based on what these states of temperature are that determines whether we're putting work into the system or the system is doing work on the surrounding. Our next goal is to find the heat transferred. Now there's a lot of ways to go about this. You can use your thermodynamic tables, but that's not necessarily the route that this problem wants you to take. And that's simply because it says that assuming constant specific heats at 375 Kelvin. Now that doesn't mean you have to go the way that I'm going to show you in this video. There are different ways you could use. There's varying assumptions that you can apply because the change in enthalpy with respect to temperature can be fairly constant, and then you can approximate that. You can use thermodynamic tables. There might be iteration processes that involve you to plug in numbers and see if that makes the equation true. If it doesn't, replug in numbers and you iterate through the table to calculate that temperature if you're looking for temperature, so to speak. So what I'm saying is that there's a lot of ways to go about these problems because you're given different methods to solve the problem. But essentially, the best way to go about these problems to be the most time efficient is to make as many assumptions, valid assumptions, that you can, which simplifies the calculation process. So in this case, the simplest way is going with the assumption that the constant specific heats are evaluated at 375 Kelvin. So you'll see why that becomes useful. Okay, and then a quick reminder, our goal is to find the heat transferred. So what we're going to be using is basically the first law again. We're going to be using this equation to define Q. So we have the first law of thermodynamics defined right here. So let's just find Q by using some algebra. So this is going to be delta U plus the specific work. And we could define delta U as simply the change in internal energy at the two different states. So this is going to be U2 minus U1. And then we're going to add the work component. Now, what's special about this, I mean, again, if you didn't recognize this, you would probably have to use the tables. But let me show you a very, a small trick when it comes to solving this problem that you may not. So we defined the work earlier as the change in pressure, or the change in specific volume times the pressure, since it's constant. So what we're going to do is write work in terms of that in this equation. So we're going to say U2 minus U1 plus, so we're going to say PV2 minus PV1. And all this is in terms of the entire mixture. It's not in terms of its components. This is the entire mixture. And then I'm going to rewrite this so it may look a little bit more familiar to you. So this is going to be, now you may or may not know, you should probably at least remember this when I say it, is that enthalpy is defined by pressure times specific volume times the specific internal energy. So this is specific enthalpy. So what that means is that we could simplify this equation even more by saying this is H2 minus H1. Now we could use the assumption that is stated within the problem statement. So this is another definition that you may have to remember from thermodynamics, is that the change in enthalpy with respect to temperature is defined by the specific heat at constant volume, so CV. So this is just a definition. And we could assume that this is fairly constant, so we could say that this is delta H over delta T equals CV. So therefore, we could say that the change in enthalpy from state 1 to state 2, or state 1, is equal to CV times the change in temperature. So T2 minus T1. So that's where we could use that assumption and write the heat in terms of this equation. So we could say that Q is simply CV times T2 minus T1. Now, one thing to note is that this specific heat at constant volume is in terms of the entire mixture. So this is the mixture. That is very important to know. So we are given T2 and T1, but we're not given CV. So that's our next goal, to find that constant specific heat for the mixture. So you might be asking, how do we find CV of the mixture? So that's a very good question, and it's pretty intuitive, I would say. And that's because when you deal with mixtures that don't react with each other, you can define the property of the mixture in terms of average weighted values, or the weighted average of that property. So what I'm saying is that we can do is find the mass fraction, which we already did, of O2, and multiply that by the CV of O2, and then we simply add the other component, the other weighted part, which is the mass fraction of N2, and then multiply that by CV of N2. So that should be pretty straightforward. And the reason why I'm using mass fractions instead of molar fractions is because CV is defined in our tables in terms of mass. Therefore, we have to use the mass fraction. If it was determined in molar units, so in terms of moles, we wouldn't use the mass fraction. We would use the molar percentage, which would be YO2 and then YN2. So we wouldn't use this if it were molar. And I denote molar in terms of this bar above the value. So that's what you do in mixtures. You basically solve the property of the entire mixture by taking this weighted average. So the next thing to do is look up these values in the table, and hopefully that we can find those values at the specified temperature. So in the problem, it's stated that CV is constant. It's assumed that CV is constant and use the value at 375 Kelvin. So unfortunately, let me just give you the table. Okay, if you look in the back of the book or any of thermodynamic tables for ideal gases, they'll provide the specific heats at specific temperatures, so in terms of Kelvin, as it did in this table. And the problem here is that we don't have the 375 that we're looking for. That's unfortunate because that means we have to do some linear interpolation. Now, if you're on an exam or maybe even just doing homework, in this case, it's not very necessary to do linear interpolation because it is a very tedious process and time consuming. If you recognize that these values are very small in terms of the change, so here it goes from 744 to 747, and we know that 375 is in the middle of these two values based on these temperatures. You could say that this is going to be roughly, what, 0.7555 or so, and that'll be a good estimate of this value of CV. And the same goes for CO2, although it's more of a drastic difference, but it's still, roughly 0.725. It's nothing too insanely different that will make your answer different from the textbook or from the final answer on an exam. If you're under a time constraint, just estimate the value from the text table. But since this is a video on YouTube and it could be sped up if you wish to, we're going to perform linear interpolation. And some people may not understand how to do this process, and that's all right. So I'm going to show you how to do this. So once you know how to do it, you can basically plug this into Excel or to a program. You could write a program, or even there's online websites or software or web applications that do this for you. So you can just plug into there if you want. But this is basically what you do to do linear interpolation by hand. So let's just, so our goal is to find CV of the mixture. So what I like to do is draw a chart, some X and Y axis. And usually I put the variable or the independent variable on the y-axis, which is typical of most charts, which is basically the variable that I'm looking for. So my goal is to find the CV values at 375. So I'll label the independent variable as CV. And then the dependent variable in this case is the temperature. We'll plug in 375 into the equation that we find, and then we'll get a CV value. Okay, so that's what I'm going to do. So the next thing I'm going to do is define these points. So this is going to be point 1, and this is going to be point 2. I drew it with a positive slope. It doesn't necessarily have to be a positive slope. It could be a negative slope. That is completely fine. The general formula that we're going to come up with will take into account of that negative or positive slope. So it doesn't matter how we draw this line. So what we do, so our goal is to interpolate between these 2 points. So we want to draw a linear line, or just a line that connects these points, because the graph or between these 2 points might actually curve like this, or any other combination that you could think of. So our goal is to just approximate it by just a line. So the next thing I'm going to do is define these points. So this is going to be T1, CV1, and this is going to be T2, CV2. And these values are based on what we got from the textbook or from the table. So we'll do nitrogen first. So this is going to be our CV1. It's going to be our CV2. And then when we do the carbon dioxide calculation, this is going to be CV1 as well, and this is going to be CV. So we'll use this equation for nitrogen, and then we'll use it again for carbon dioxide. So our goal is to find this value right here. So we'll say this is the temperature that we're trying to find. So in this case, this will be 375 Kelvin. Okay, so this is what we're going to be plugging into the equation to get the C value that we're looking for. So this is the C value at 375 Kelvin. So our goal is to find that Y value. So this is a very simple problem. It's really a geometry problem if you recognize this. So I'm going to go through all the details. So this is going to be the line that we just drew on the graph. And this is going to be that middle point. So what you want to do is basically create right triangles, and this is the reason why is because the slope of these triangles are the same. So we could draw this big right triangle here. This is a right triangle, and then we can draw a line downward, and this is going to be a right triangle. So since these triangles have a right angle and they share the same angle right here, that must mean all the angles are the same, so like that. Therefore, what we can do is use the idea of similarity or proportionality and write out an equation to solve for this C value. Okay, so what we want to do is say that this length, so we'll call this length right here. So that length is going to be this right here. So that's simply T minus C1. And then this height is going to be CV minus CV1. And then this entire length over here is going to be T2 minus T1. And then this is going to be CV2 minus CV1. So again, since these triangles are similar, what we can do is write this proportionality. So we can say that the ratio of CV minus CV1, which is this length, with respect to its other side length of T minus T1, must be equal to this length, so CV2 minus CV1 divided by T2 minus. So let's just use an idea of proportionality. Our goal is to find CV, so we just solve for CV by doing some algebra. Okay, so if you solve for CV, it's actually a function of temperature. So this is our independent variable without the subscript. That's our independent variable, or actually dependent variable. And that means that whatever value we plug in can be interpolated between these two values, T2 and T1, or CV2 and CV1. Basically, we have a function of the specific heat in terms of temperature. And you know you did it right because this is actually the formula for the point-slope equation. So if you have a point, you have a slope, you can define a linear equation or by this equation. We basically have everything we know. We have all these values based off the table. So this is going to be, I forgot to define these. So this is going to be T1 and this is going to be T2. We plug in our dependent variable, which is the specific heat we're trying to find at that specific temperature, which is 375. So we have everything we need to know, and all we have to do is plug in. Since this video is probably going to be very long, I'm going to save us some time by just writing out the CV values. So just plug in all these values into this equation, and you should get the same thing that I'm going to write right now. Okay, so what we get is 0.746 for nitrogen and 0.728 for CO2. Now, I just want to, make this super clear, and let's look at the chart and compare these values. Okay, so I would have, just assumed some arbitrary value between 7447 and 74, if I said that correctly. So what we got was 0.746. That's roughly 0.745. It's, it's fine. It's a good estimate if you just eyeballed it. If you look at this is, I said earlier it was like roughly 0.725. We got 0.728. It's best to recognize how to save time, recognize that the changes are very small, so therefore linear interpolation is usually not the best route, because you could estimate. Now, if this is like your job or something, and you need these significant figures, and yeah, obviously do the interpolation, but usually there's software to do that. We got our CV values, now we could find the mixture of the CV values. So you plug in these values from the chart from the very beginning of this video, and then the CV values that we just found, and then the change in temperature, which is given in the problem. After plugging in all these values, what you get is negative 99.224 kilojoules per kilogram of the mixture. Okay, and then just to make this point even further, let's, validify this negative value. So let's go back up to where we defined our system. So we got okay, let me rewrite the value. So we got negative 99 kilojoules per kilogram. We got a negative value for the heat. So based on how we defined our sign orientation, we said that if Q is negative, heat is leaving the system. Okay, so we got a negative 99, which makes sense because in the problem statement, it says that the mixture is cooled. Therefore, heat must be leaving the system. And that is it for this problem. This is a very, very good problem in terms you really have to know the details of, thermodynamics, what to apply, the ideal gas law, understanding how to use weighted averages to find the values you're looking for in terms of mixtures, and so forth. So this is a very good problem to study mixtures, at least for closed systems. So hopefully I helped you with this. With that being said, I'll see you in the next video.